Modeling with linear functions. When modeling scenarios with a linear function and solving problems involving quantities changing linearly, we typically follow the same problem-solving strategies that we would use for any type of function. Problem-solving strategies. 1. Identify changing quantities and then carefully and clearly define descriptive variables to represent those quantities. When appropriate, sketch a picture or define a coordinate system. 2. Carefully read the problem to identify important information. Look for information giving values for the variables or values for parts of the functional model, like slope and initial value. 3. Carefully read the problem to identify what we are trying to find, identify, solve, or interpret. 4. Identify a solution pathway from the provided information to what we are trying to find. Often, this will involve checking and tracking units, building a table, or even finding a formula for the function being used to model the problem. 5. When needed, find a formula for the function. 6. Solve or evaluate using the formula you found for the desired quantities. 7. Reflect on whether your answer is reasonable for the given situation and whether it makes sense mathematically. 8. Clearly convey your result using appropriate units and answer in full sentences when appropriate. Example 1. Emily saved up $3,500 for her summer visit to Seattle. She anticipates spending $400 each week on rent, food, and fun. Find and interpret the horizontal intercept and determine a reasonable domain and range for this function. In the problem, there are two changing quantities, time and money. The amount of money she has remaining while on vacation depends on how long she stays. We define our variables, including units, output, M, money remaining in dollars, input, T, time, in weeks. Reading the problem, we identify two important values. The first, $3,500 is the initial value for M. The other value appears to be a rate of change. The units of dollars per week match the units of our input variable divided by our input variable. She is spending money each week, so you should recognize that the amount of money remaining is decreasing each week and the slope is negative. To answer the first question, looking for the horizontal intercept, it would be helpful to have an equation modeling this scenario. Using the intercept and slope provided in the problem, we can write the equation m of t equals 3,500 minus 400t. To find the horizontal intercept, we should set the output to 0 and solve for the input. 0 equals 3,500 minus 400t. T equals 3,500 divided by 400 equals 8.75. The horizontal intercept is 8.75 weeks. Since this represents the input value where the output will be 0, interpreting this, we could say, Emily will have no money left after 8.75 weeks. When modeling any real-life scenario with functions, there's typically a limited domain over which that model will be valid. Almost no trend continues indefinitely. In this case, it certainly doesn't make sense to talk about input values less than 0. It is also likely that this model is not valid after the horizontal intercept unless Emily's going to start using a credit card and go into debt. The domain represents a set of input values, and so the reasonable domain for this function is 0 less than or equal to t less than or equal to 8.75. However, in a real-world scenario, the rental might be weekly or nightly. She may not be able to stay a partial week, and so all options should be considered. Emily can stay in Seattle for 0 to 8 full weeks and a couple of days, but would have to go into debt to stay 9 full weeks. so restricted to whole weeks. A reasonable domain without going into debt would be 0 less than or equal to t less than or equal to 8, or 0 less than or equal to t less than or equal to 9 if she went into debt to finish out the last week. The range represents a set of output values, and she starts with $3,500 and ends with $0 after 8.75 weeks. So the corresponding range is 0 less than M of T less than 3,500. If we limit the rental to whole weeks, however, the range would change. If she left after 8 weeks because she didn't have enough to stay for a full 9 weeks, she would have M of 8 equals 3,500 minus 400 times 8 equals $300 left after 8 weeks, giving a range of 300 less than or equal to M of T less than or equal to 3,500. If she wanted to stay the full 9 weeks, she would be $100 in debt, giving a range of negative 100 less than or equal to M of T less than or equal to 3,500. Most importantly, remember that domain and range are tied together, and whatever you decide is most appropriate for the domain, the independent variable, will dictate the requirements for the range, the dependent variable. Try it now. A database manager is loading a large table from backups. Getting impatient, she notices 1.2 million rows had been loaded. 10 minutes later, 2.5 million rows had been loaded. How much longer will she have to wait for all 80 million rows to load? Example 2. Jamal is choosing between two moving companies. The first, U-Haul, charges an upfront fee of $20, then 59 cents a mile. The second, Budget, charges an upfront fee of $16, then 63 cents a mile. When will U-Haul be the better choice for Jamal? The two important quantities in this problem are the cost and the number of miles that are driven. Since we have two companies to consider, we will define two functions. Input, M, miles driven. Outputs, Y of M, cost in dollars for renting from U-Haul. B of M, cost in dollars for renting from Budget. Reading the problem carefully, it appears that we were giving an initial cost and a rate of change for each company. Since our outputs are measured in dollars, but the cost per mile given in the problem are in cents, we will need to convert these quantities to match our desired units. 50 cents a mile for U-Haul and 63 cents a mile for Budget. Looking to what we're trying to find, we want to know when U-Haul will be the better choice, since all we have to make that decision from is the cost. We are looking for when U-Haul will cost less, or when Y of M less than B of M. The solution pathway will lead us to find the equations for the two functions. Find the intersection, then look to see where the Y of M function is smaller. Using the rates of change and initial charges, we can write the equations. Y of M equals 20 plus 0.59 M. B of M equals 16 plus 0.63 M. These graphs are sketched to the right with Y of M drawn dashed. To find the intersection, we set the equations equal and solve. Y of M equals B of M. 20 plus 0.59 M equals 16 plus 0.63 M. 4 equals 0.04 M. M equals 100. This tells us that the cost from the two companies will be the same if 100 miles are driven, either by looking at the graph or noting that Y of M is growing at a slower rate. We can conclude that U-Haul will be the cheaper price when more than 100 miles are driven.